hour, actually we need to consider 24 different workload distribution, and we need to perform the capacity planning over the 24 hours for the application. So we need to solve 24, in that case, 24 NPR problems. What we have done is we have formulated the problem, we formalized the problem, and we have shown that this is actually an NPR. It is actually equivalent to a B-level programming problem. So just to have an intuition of this kind of problem. A B-level problem, we have a B-level problem when actually the decision variables are split into different families, and one decision has some impact on the effect of a linear problem. So let's consider an example. Imagine that you have a company, you have agents, and these kind of agents need to visit your customer in the territory. So what you do is maybe the first problem you have is to assign your agents to the customers, and then the second problem could be you need to schedule the visit of your agent to the customer. So the first assignment could be an NPR, and the decision of this first assignment of agents has an impact on the schedule that you need to optimize. So this is an example of B-level problem. So the tool for solving the capacity planning in such system is MODAClouds. This is the acronym of MODAClouds, and we can support the performance evaluation. The main tool that we use in the design space exploration is Line, but we can also use different other solvers that could be specific for other quality of service methods that we want to consider. Internally, Space4Cloud adopts Palladio component models, and the solution that we have performed and implemented is a meta-heuristic solution that iteratively improve a current solution. Actually, we identify this meta-heuristic. Usually, the performance of these meta-heuristics depends on the quality of the initial solution you get. So what we do is we identify a promising initial solution by formulating a simplified model that we can optimally solve through standard mixed integer linear programming solver. And then we have this B-level, we have implemented also B-level tableau search that iteratively improve such kind of solution. This is how our system is built. Actually, we have some enriched Palladio model as input that has specified the workload profile over the 24 hours, for example, the characteristic of the random environments. And we have also a set of cloud providers that are candidates for the final deployment. Then actually, through this iterative method, we interact with the performance solver to evaluate every candidate solution. And then at the very end, we will identify the final deployment. So if we start, for example, from a set of candidates that are Amazon, Google, and Azure, one solution could be, okay, you just need for your application, given some quality of service requirements, you just need the Amazon and Azure. And then, imagine that you have several users, you decide for every hour how to split these users in these two clouds, and for every tier of the application, you know which is the best type of the VM to use, and how many VMs to use for every hour of the day. So this is the output that we get from our tool. Before entering in the technicalities, actually, we did also some work at the modeling level, because we need to actually specify some CPM, CPS models for modeling the resources of cloud provider and their cost. Then we need to map this CPM, CPS model into our extension of Palladio performance models in order that we can perform the analysis. We need also to specify some models for quality of service constraints, and also for architectural constraints. So I will not enter in the details of these meta models. I will just provide some examples. If we consider the Modello case study, actually what we can do is we have an SVN server. We can predicate on the average response time, or maybe on the percentile distribution of the response time of the commit operation. So we can say, okay, on average the response time is less than 1 minute, while 85% of the requests need to be completed in less than 5 minutes. Then we could have some, in multi-cloud provider, for every hour of the day, you have one minimum cost provider. So if you want to force the use of multiple providers for availability reason, you can say, okay, at least a given percentage of the individual of the end users need to be supported to a given cloud provider. Then we can also include some explicit constraints on availability. So we can say, okay, the final deployment availability should be at least 4 9. Then we have some constraints that predicate lower level metrics, so we can specify the maximum utilization of the CPU of a given tier. We can specify the minimum memory to be allocated to an application. We can specify the replica number. So this is important. We can specify the minimum and maximum number of replica in a way that these are equal to 1. For example, if we have a legacy component that cannot scale. And finally, we can also specify the candidate configuration for the provider. So we can say, okay, I want to use or I want to exclude some given instances of a given provider. Okay, we will show later how to specify this quality rate constraint, maybe. Yeah, because I need to hurry up. So for what concerns the initial solution, we have modeled this as a mixed integer linear programming model. I will skip the details. Actually, what we do is we consider the distribution of the end users over the 24 hours, and actually we need to do some simplification because line is a numerical solver. The problem is that through Equian models, performance models, we don't have closed formula that can say, okay, given a configuration of the system, which are the response time or the response time distribution. Then what we did is we have simplified the performance model that are based on some MG1Q that are the standard models that are used in performance analysis. We cannot consider the random environments, but we can include the quality of service constraints and architectural constraints. And actually we have obtained a very fast initial solution through the Simplex solver, but we are working on this. We can use also open source solver and plug the milk solver that we want. This initial solution then is refined by a tabu search algorithm, and actually the tabu search is an extension of the local search, just to have a flavor of how this method works. So the local search actually is an iterative algorithm that started from a current solution through atomic moves, consider some other candidates that can be associated by changing the configuration of the current state. And then the next step, of course, here we are trying to maximizing our objective function. And then, so we move the next solution will be the best one that we have in the neighborhood. And then we directly improve our current solution in this way. And of course, one of the points that we get is when we find the local optima, we get stuck in this local optima. So we cannot find probably a better solution that would be close to this one. So to avoid this, what we did is we have implemented this tabu search that has two main concepts. The first concept is that it can accept some worsening moves in a way that we can escape from this local optima. And then we have also a short memory, which is the tabu list, that stores the configuration of previously visited solutions in a way that we can really avoid to go back to previous local optima. So again, what we do is we have a neighborhood, we evaluate our neighborhood through atomic moves. Then here, for example, we improve and we go there to this local optima. And then what we do is we evaluate the neighborhood again, and in that neighborhood we will escape, we will accept worsening solution. And here we evaluate the neighborhood, and we don't go to the red dot, which is because this is stored in the tabu list, and this way we can escape from this local optima and avoid the two-cycling. And so this way we go. This will be our next point, and through this we will go to the other part of the curve or the function. We will find better optimal solution. Of course, we cannot guarantee that we will find any global optima because the method is not feasible with that.
So is the tabu list only one step?
No, you can configure, it's around 7 or 10, and this is a parameter of the optimization. We are fine-tuning also this. So what we did is we have implemented a B-level tabu search. So actually, the main idea is we, through small moves, let us say, we find, so we try to improve our current solution. Then when we got started in a local optima, we will perform a disruptive move that it will significantly change the current solution. Sometimes we lose also the feasibility, so we go to violate the constraints, but this will help in diversifying the search. And of course, we will provide the best solution that that satisfy the constraint. So this is behaving in a sense. So the high-level move is change a type of VM, while the low-level move is the small move is increase the number, so perform the scaling and scale out of the VMs that we have here, or maybe change the border. Since we are considering multiple providers, we try to move some users from one provider to another to try to improve the cost of the solution. So I will skip the details on the architecture of this because I want to devote more time to the case study, to the constellation case study that we had. So usually in this kind of analysis, the first question you try to answer is, what is the system bottleneck? And we have seen that this can be also obtained using line directly, but I will show you now how to use Space for Cloud also to get these answers. And then what we do is here is a study of the constellation configuration in a way that we want to understand what happens if we vary the number of users, and so we want to understand how the configuration changes and also the cost. And so this is the reference workload that we are considering because I told you we will solve the capacity planning problem for every time, for every hour of the day, and this is the basic shape that we are considering. Is a bimodal distribution. We took this from a real large web server, since we don't have, since this is under development. Right now we don't have the end users distribution for the model case study. So actually, I have a demo for this. I will show you how to. Oh gosh, I'm going to the landscape. So actually, this is Space for Cloud. This is an Eclipse plugin. It's built on Palladio Bench tool, and actually so these are the models that can be obtained through Modelio. There is a feature that shows how to export the models of our application, and we export directly in our extension of the Palladio models. And then actually we can run by simply, okay, good, let's change it. So here, to speed up the demo, here we should specify again where are the repository models, the allocation models, and so on and so forth, all the models that have been discussed by Juan. We can load a configuration. This is the one for the assessment. Then we start the analysis, and here we are running actually, okay, here it is. Here it is already a result. So here what we have is, for every hour of the day, we know how the average response time varies for the individual services that are provided by the Modelio case study. And here you can see how also is the utilization of individual containers. And you see here, we have seen before that the bottleneck actually is